Today I'm going to talk to you about parity. And so where does parity fit into the computing course that you're currently doing? Parity fits in when we talk about data transmission. So we have talked about different ways of transmitting data between devices, and parity fits into that part of the unit. So what we're going to talk about today, so we're going to remember that we've got two devices. This can be device A, this can be device B, and they are connected together, and what we want to do is we want to transmit some data between the two of them. Okay, now the data that we're going to transmit between the two of them is the letter S. Alright, in fact specifically the capital letter S. Now, if we go to the ASCII table, okay, which you can hopefully be able to see in the top right hand corner of the video, alright, if you go to the ASCII table, you will find out that capital S is in fact, in decimal, is represented as the number 83. Obviously, we like the number 83, but the computer won't like the number 83, so we now need to convert this into binary. Now, if you remember rightly, when we talked about ASCII, okay, each ASCII character is worth 7 bits. So I'm going to draw 7 squares, which we can use to put in our ASCII character. So we've got 4, 5, 6, and 7. Okay, so we're going to make 83. So we've got the decimal number 83. Let's just do a quick revision, see if you remember how to convert it into binary. So I'm going to start by writing my powers of 2 from the right across. Okay, so I'm going to start with 2 to the power of 0, which is 1. I'm then going to go 2 to the power of 1, which is 2. 2 to the power of 2, which is 4. 2 to the power of 3, which is 8. 2 to the power of 4, which is 16. 2 to the power of 5, which is 32. And then finally 2 to the power of 6, which is 64. Okay, so I've got 7 bits. Now what I want to do is I want to make the number 83. So again, this is just revision. Alright, what do we need to make the number 83? Well, if I start from the left, do I need a 64 to make 83? Of course I do. Okay, so I'm going to put a 1 in there. Do I need a 32? Well, 64 plus 32 is 96. That's bigger than 83, so I don't need a 32. Okay, do I need a 16? Well, 64 plus 16 is 80, so yes I do. Okay, because that's less than 83. Now I've got 3 left, so do I need an 8 to make 3? Of course I don't. Alright, so I'm going to put a 0 in there. Do I need a 4 to make 83? No, I do not. Do I need a 2 and a 1? Of course I do, so I'm going to put a 1 in there and a 1 in there. Okay, so hopefully you will agree with me that 83 in binary is 10100111. Okay, so that's my 7 bits of data that I want to transmit. Okay, now what I'm going to do is I want to make sure that what I transmit is what's received. So I want to make sure that what is sent from computer A is received by computer B. Okay, so what I'm going to do is I'm going to add a parity check. Okay, so I'm going to add a parity check. Now what happens when I add a parity check is my 7 bits are going to go from 7 bits to 8 bits. Okay, hopefully you remember what 8 bits is. Okay, 8 bits is a byte. Okay, so I'm going to go from 7 bits to 8 bits. Okay, so I'm going to draw, this time I'm going to draw 8 boxes. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, so my 7 bits of data is going to become 8 bits of data, or a byte of data. Okay, now just an extra little bit that you need to know is I'm not going to put my number in yet because I need to decide where I'm going to put my parity bit. So I'm going to add an extra bit and I need to decide where I want to add it. Okay, and this is in fact something that computer A and computer B will need to agree upon. All right, and when these two will transmit data between the two of them, they will do something called handshaking. All right, and during the handshaking phase, they will make all of these decisions. So the first decision they need to make is, are they going to place the parity bit at the back, or are they going to place it at the front? Okay, now obviously in computer science we do like an acronym, or we do like to give it a fancy name. So we don't say the back and the front, we say that this one at the back is called the least significant bit. And this one at the front, if this one is the least, hopefully we've all got the idea that this should be the most significant bit. So as I've already mentioned, the computers during the handshaking phase will have to agree on whether the parity bit is going to be positioned at the most significant bit or the least significant bit. Okay, I'm going to use the most significant bit. So my 7 bits of data are going to go in here. So I'm going to write those in. There we go. Okay, so I've decided that I'm going to use this space here, the most significant bit space, to add my parity bit. So there are now, what we need to do is I need to discuss with you the 2 types of parity. Okay, so there are 2 types of parity, and hopefully they're very similar. There's one small difference between them, and hopefully you'll work that out from the name. So we can either use even parity or we can use odd parity. Okay, so we'll start. I'll demonstrate how to do both, and hopefully you'll understand the difference. Okay, so we'll start with even parity. So what I need to do is I need to work out what my parity bit is going to be. So I've decided, or the computers have decided, during the handshaking phase, that they're going to use the most significant bit, and they've decided that they're going to use even parity. So what I'm going to do, what the computer would do, is it's going to count the number of bits it has so far. 1, 2, 3, 4. Okay, now that is an even number of bits. We have an even number of bits. So the bit that I add as my parity bit is going to be a 0. Because I already have an even number of bits. Okay, so now when I count the number of bits, 1, 2, 3, 4, I put a 0 in there, I've still got an even number of bits. Okay, so my parity bit, in this case, was a 0. Okay, so now I've added my parity bit. The computer A, is now going to send that byte of data to computer B. Okay, so computer B receives this byte of data, 0, 1, 0, 1, 0, 0, 1, 1. Okay, now it wants to check if what it received is what was sent. So what it's going to do is it's going to count the number of bits. Okay, so how many bits are in the byte of data? 1, 2, 3, 4. Computer B knows that we're using even parity, so it counts. It has an even number of bits, 4 bits in total. That is an even number, so it must have been received correctly. Okay, so I'll just show you what would have happened if it was received wrongly. Okay, so if there was a mistake, and this was the byte of data received by computer B rather than sent by computer A, then computer B checks the number of bits. 1, 2, 3. Okay, well that's an odd number of bits, but we're using even parity, so there must have been a mistake, so something has happened. Okay, so what the computer is going to do, computer B, is going to send a message to computer A and say, can you resend that byte of data? Okay, so hopefully that makes sense. Now let's see what would have happened if computer A was going to send something different. So say computer A was going to send T, the letter T. Well, the letter T is the number 84. So this is going to change. This becomes a 1. this becomes a 0 and a 0. Okay, so imagine that we're sending the letter T. We're still using even parity, we're still using the most significant bit. So, like we did before, computer A is going to count the number of ones. 1, 2, 3. This time there are odd number of ones. We're using even parity. Okay, so the parity bit is going to become a 1. So that when you add together, or when you total up the number of ones in your byte of data, it becomes an even number. 1, 2, 3, 4. Okay, so even parity should be that when you add your parity bit, the total number of ones becomes an even number. All right, now hopefully it should be pretty obvious how odd parity works. Okay, so odd parity works in exactly the same way, just that the difference is that this time we want an odd number of ones rather than an even number. So if we go back